if PS donates the matrix that starts from different starting positions S, then we can donate this PMSJ as the largest count in the column J of PS. So we will see these details later on. Here we can see this MPS donates the maximum count within a column. So we can see here in the first column, MPS 1 means column number 1 is 5. So we write here 5. In the column number 2, MPS column number 2 is also 5. And so on. We have written the maximum MPS score of each column. So for the starting positions means this is the conserved region within a DNA sequence, and its starting position of each DNA sequence is different. So for the starting position in this figure, score sDNA is 5, 5, 6, 5, 5, 6 and 6. It's come out to be 42. This code sDNA can be used to measure the strength of a profile. So higher the number of this score, the more is the strength of this profile. And this profile is corresponding to the starting position of, that is S. And we can also calculate the consensus score of L into T. L means the size of the motif and T is the number of DNA sequences. So we can calculate the consensus motif that correspond to the best possible alignment score. So we have calculated the best possible alignment score, and this score is 42. So if we find to calculate the other possibilities of this alignment, we will get the score less than 42. So for higher score more than 42, there is no possibility within this alignment. So this is the maximum score of this alignment. So here we can define the consensus score as sDNA sigma L j is equal to 1 MPS j. So it means that we write this equation as MPS 1 plus MPS 2. We have already seen the score of MPS of each column. So the meaning of this equation is that we will calculate the MPS score of each column, and then we will calculate the last column score, and we will get the total. So the score in the last figure we can calculate. MPS 1 is 5, MPS 2 is also 5, MPS 3 is 6, and so on. We will add the values of all the MPS, and MPS 8 will be 6. So I have skipped within this, so it comes out to be 42. So we can also, I have told you, can calculate the consensus score of this alignment, and a consensus score of this one is however correspond to the worst possible alignment, because it contains all the mix of the nucleotides. It means that adenine, thymine, cytosine and guanine, they will be present in equal ratio, and it is represented by L multiplied by T by 4. So this consensus score will be much lesser than the other possibilities of this alignment. So in this simplest form, the motif finding problem can be formulated as selecting starting positions S from a sample that maximize this sDNA score. So here we can calculate, or we can write the algorithm to find the motif finding problem. So here is the goal. Goal is a given a set of DNA sequences. It could be any number, and we have to find a set of Elmers. Elmers means the conserved region within a DNA from each of the sequences that maximize the consensus score. So we have to calculate the Elmer sequence with the maximum consensus score. So the algorithm, we have to input some values, and it will be a T into N. So T is the number of DNA sequences and N is the number of that specific motif. Matrix of DNA and the length of pattern to find. So we have to find the pattern, and we will get the output in the form of an array of T starting positions. T is the number of DNA sequences and S is the starting position, S1, S2 up to the last ST. And what we will get is the maximum score of that alignment. We have seen that we can calculate the maximum consensus score within the DNA sequences having a specific motif length. By doing so, we will get the maximum score of the DNA.